Welcome to the lesson number 8, the user identity mapping. So in this lesson we are going to see what is the user identity mapping in general and how it works conceptually. We do not have here also the demo videos because the explanation of the concept requires pretty much of the time, so we will be out of time if we are going to demonstrate how to configure the user identity mapping on each of next generation firewalls we had a chance to deal with here. And the configuration itself requires several options, several parameters on several places, on each of different places and different way in each of the firewall manufacturers. And also we should set up an Active Directory in a lab environment. So we will stick to the conceptual explanation because it will be very useful to understand better the admin manual instructions for user identity mapping configuration for the next generation firewall of your choice. Okay, so what is the user identity mapping? It's a capability of a firewall to actually use the usernames or groups or user groups, such as in this example, finance group from Active Directory, let's say, instead of the IP addresses as a source IP addresses from our clients. Why is this useful? Well, I'm sure that you have also the users in a different subnet, the users getting assigned different subnets depending on the way how they connect to the enterprise, to the organization. For example, if they are connected through the laptop docking station using a wired connection, they are assigned one subnet. While they're going to the Wi-Fi, then they will be assigned a second subnet. And when they are on the VPN side of a remote connection, then they might have using a third address range. So, and plus you maybe have some traveling users. They're traveling around the enterprise. And if you have a lot of branch offices, then if you want to maintain the same firewall policy, no matter from where user originates, then you need to have your firewalls, then you need to have covered all these subnets as a source addresses in your firewall policy, which is simply just not scalable enough. So instead of that, it's a nice thing that you can use the user groups or usernames, but the user groups are more flexible way instead of source IP addresses in the firewall policy. So for example, we have a simple firewall policy which says allow group finance to the internet and block everything else. So now our firewall doesn't care, or the administrator of this firewall doesn't have to care about the origin IP address of the users. He just needs to care that for example, the John is in the finance group. As long as our John is in a finance Active Directory group, he will be able to access the internet. So how actually firewall maps, the mapping of the IP address with the user identity is actually what we are calling the user identity mapping feature. So how exactly the users are mapped to the IP addresses, we will see in the next slide when we're going to talk about the user identity mapping concept. Okay, so the concept of the user identity mapping. First, we need to explain a couple of components we have here. First of all, we have a firewall. Here on this graphic, it's represented by the name ASA. Actually, this is because I borrowed this graphic from my another course dedicated to Cisco ASA, Adaptive Security Appliance Firewall, but I've just the clarification for you is just that it can be any firewall nowadays on the market supports that feature. ASA is even not a true next generation firewall, but it still supports the user identity mapping. But somehow the user identity mapping actually broke through with the next generation firewalls. But ASA, although it's not a next generation firewall, adopted this feature as well. So when you see the ASA on these graphics, consider it as a firewall. Okay, so we have a firewall. We have the endpoint user in our local network that it's using a computer joined to the Active Directory domain. But instead of the Active Directory, it can be any LDAP system. Majority of organizations simply use the Active Directory from Microsoft. We have also the Active Directory domain controller computers. They are a vital component of the solution. Also, we have the AD agent. It's a separate piece of software deployed on the dedicated machines in the network. So it's not deployed on the end user station, but it's deployed on the dedicated servers or computers, whatever you like. I advise you to deploy them in a multiple copies for the sake of redundancy, and also the communication between the Active Directory domain controllers and the AD agent component can be kind of a heavy on a bandwidth. So if you have some kind of low bandwidth links, I advise you to deploy AD agents on these remote sites as well. The AD agent software is usually a free. I think it's a free, almost free, or free for the most of the next generation firewall vendors. So you can literally deploy them as many as you want. So let's see how things work. First, the firewall needs to obtain an user to group mapping from the Active Directory. It uses the LDAP protocol to download a list of users and their respective groups. This is why, because we need to. Usually you want to use user groups in your firewall policy instead of single usernames or dedicated usernames because of simplicity and the flexibility. So the firewall gets the information about which user belongs to which Active Directory group, and this information is obtained periodically. Okay, so what happens next is that the end user authenticates with the Active Directory, and upon the authentication, the Active Directory logs the information about current user IP address and the username into its security event log. And the AD agent software is subscribed to these information, so it pulls them periodically to get the informations about usernames and their current IP addresses and supply these information. It uploads these information to the firewall. So now the firewall maintains two tables. So first table is the user to group mapping, so membership of each users in their respective groups. And it also has another table thanks to the AD agent, which contains the username to IP mappings. So now we have our policy, all group finance to the internet, and we have our user John, who is just logged in to the Active Directory successfully. So when the firewall sees a packet sourced from this IP address, for example, it will take a look into its user to IP mapping table to see if it knows about this IP address, to check if this IP address is bound to some username. So it finds out that this IP address is bound to the John username. So now it just needs to check the user to group table, check to find out which group John belongs, and the firewall finds out that John belongs to the group finance. So this packet from the IP address, from this IP address 192.168.1.3 is actually belonging to the John, which belongs to the group finance, which is according to the firewall policy allow rule. So the firewall will allow this session because all the users from the finance group are allowed to go to the internet, and will block anything else. So I hope that I managed to bring you a little closer this concept about user identity mapping, because in the next video we're going to see some challenges that you can run into when you're deploying and using the user identity mapping on your next generation firewall. So stay tuned. Okay, let's see what are some challenges when we are using the Active Directory and the user ID mapping. Well, first, what can happen is that if you have users that are idle too long, which means from the Active Directory perspective, idle too long, what this means is that the let's say if you have a user which doesn't do anything with the Active Directory for a longer period of time, so it doesn't access any file shares or printers or exchange mailbox or log off, log on to the domain, what happens is that since the Active Directory log, domain controller logs, are based on the first input, first output concept, which means that the oldest records are being overwritten with the latest records in order to save the log storage. So let's say that you have a John, our John, that is a little bit lazy that day. He doesn't do anything with the Active Directory, and it's just expire. Its records in the Active Directory domain controller log just are being deleted, and the temporary firewall will not be able to map the John's IP address to its username because it's got a fresh information from the AD agent software that says that IP address, this particular IP address, is not longer bound to any username. And if the John just opens the web browser without initiating any action against the Active Directory, such as authentication or access to the file share or similar tasks, and its browser will generate a request to the internet from the IP address 192.168.1.3. The firewall will simply not be able to match that IP address with the particular username nor the particular group as a consequence. So what will happen is that the traffic from the John's computer will end up in the second rule, which says block everything else. So the John must do something with the Active Directory from time to time just to refresh its log appearance in the Active Directory domain controller log. The other option to fix that is just to increase the login session idle timer on the AD Agent software itself. Please consult your AD Agent software and next generation firewall manufacturer's manual about how to do this. It's usually just a single option to change the value on the single option. It's nothing complex. Okay. The second thing is the nasty one. The AD admin, Active Directory admin, makes uncoordinated change. Well, once I had a case when my customers called me in a panic, it's just, okay, none of my users cannot access anything behind a firewall or into the internet or the DMZ segments. Nothing works anymore. What happened is that the firewall actually, when we came to the site, we saw that the firewall is actually not able to map any source IP address from a packet to any username. What happened at the end is that the Active Directory administrator made a change without communicating that change to the networking and firewall team. It just simply moved the location of the domain controller's log file to the another disk drive. And the only thing what we needed to do is just to restart the AD agent to reconnect to the Active Directory domain controller to just start reading the log from the another location, from the new location. But until we did so, any firewall simply blocked any access through it because all their security policy or all their firewall policy was based on the user identity, not on the IP addresses. So this user identity mapping thing kicked them in the face, nasty, and they had a major outage of the network. So yeah, well, if you are using the user identity mapping, please let your Active Directory or domain controller administrators knows that when they change something, when they are doing something with logs, it might affect network connectivity. Okay, and then we have the remote desktop sessions issues. Well, let's say that you have a DNS server, and let's pretend that it's a Windows server, so it has a remote desktop service on it for the remote administration. And now if you have an administrator with the username admin who logs into the remote desktop of that DNS server, if by default the firewall will start to map, or the user agent software will map, or domain controller will map actually the IP address of a DNS server to the currently logged user, which is, in this example, admin. So the firewall will use the firewall policy when the Active Directory admins are stated as a source to allow traffic from this DNS server. And this might be not something that you want. Okay, so the way how to deal with this is just simply, you can, on the user identity agent on every firewall manufacturer, you can simply disable a particular IP address, like a DNS servers or whatever servers you are logged in with the remote desktop, from the user to IP mapping. So since these servers has DNS server particularly, or DHCP server, these servers are usually with a fixed IP address, so you can continue using IP address based firewall policy for these servers. So you do not have to, and it's not advisable to do to create firewall policies for these servers based on the user identity, because it can happen. I've just told you what can happen. So if so, you just need to make exceptions for the IP addresses of the remote desktop servers in your environment. This exception is done in the user agent software configuration. Okay, it's a remote desktop session. Terminal server case, the terminal servers, these are terminal servers based on the Citrix or remote desktop protocol. It's just like a VDI, virtual desktop infrastructure. When you have multiple users, which are not using their desktop for PC for the work, but they are instead connecting to using their thin clients, connecting to the virtual desktop infrastructure, to their virtual desktops using the terminal server. It's usually a remote desktop protocol, but anyway, they are using the terminal server to do their work. So all the traffic coming from these users originates from the terminal server's IP address. And if you want to have separate firewall rules for these users, then you will have a problem, because all the traffic is sent from the single IP address, that is the IP address of a terminal server itself. So to fix that, you need to deploy a different kind of a user agent software, which is a special terminal server user agent software, which is deployed directly on each of terminal servers. And what it does, actually, it assigns a range of source ports, TCP and UDP ports, for each logged in user. So, for example, we have a terminal server user John, or John again, who's assigned its respective source port range. When the firewall sees a TCP or UDP packet from that particular source port range, it will immediately know that this traffic belongs to the user John, and it will then apply its firewall rules accordingly. And the another case, all these cases are something that I've experienced during my career. Okay, so last thing I saw is a login as a service issue. Well, it's not a common issue, but it's worth saying something about it. What happens if, for example, when I saw that when the users had soft phones, that is the IP phone software, IP telephone software deployed on their workstations, and the Windows service responsible for that IP phone it was running under a username different than the currently logged in user. So let's say that we have our user John, who is logged in into their computer, but his software IP phone application installed on his workstation is actually, its service is working as a user Sam, for example. So the user John logs into the computer and starts working, with the internet. So firewall maps its IP address successfully with the username John, and everything works as expected. But now the John activates its software phone, and what happens next is that suddenly the Active Directory sees the IP address of the John's workstation mapped as a user Sam. And then firewall will not able to apply a firewall rule for a user John, but it will apply. What might happen is that the firewall can apply rule for a user Sam, for example, which might not be something that you want. Of course, this depends on the order of the firewall rules on your firewall, but it can happen. So the way to do this, the way to resolve this is to exempt a particular usernames. These are usernames that are used for running services on your workstations from the user identity mapping. Similarly, what we done here for the remote desktop sessions, but here at the remote desktop sessions problems, we were making an exception for the remote desktop server IP addresses from the user identity mapping. Here, on the login as a service issue, we are making exceptions for particular users to be exempted from the user identity mapping. Both of these exceptions for resolving a login as a service issue and the remote desktop server sessions issue, both of them are configurable at the user agent software. Okay, so let's wrap it up. So at the end, let's conclude this session about user identity mapping. Well, first, user identity mapping enables us to have a firewall policy based on the user identities instead of the IP address, which can be practical and flexible. In the case of a terminal server, we have the special kind of user agent software assigned source port ranges allocated per user. So when the firewall sees a packet, TCP or UDP packet, sourced from a port which belongs to a particular port range, it knows that it belongs to the particular user. So it can apply the firewall policy accordingly. And watch out about the Active Directory setup, and you need to always coordinate changes with your Active Directory team because you don't want to uncoordinated change on the Active Directory side disrupts your network connectivity to your firewall. So that's it. Goodbye.
Hello and welcome to OWASP Top 10 Security Fundamentals first session. It's a pleasure to have you on board. This is the first part of World Wide Web Fundamentals session. I want to quickly introduce you to OWASP and its projects. You may have heard about OWASP before. OWASP stands for Open Web Application Security Project, and despite formally being a non-profit organization, it is in fact a huge open community. There are over 275 local chapters, and I strongly encourage you to join yours. You can also attend one of the worldwide conferences or join the mailing list to be always up to date with news and events. OWASP has had a very important role bringing security awareness and education to the software development industry. It offers handful application security tools and standards, complete books on application security testing and secure code development and review, cheat sheets on many common topics, and many more open source community-led projects. You'll find detailed information at owasp.org. Visit the website and browse all available projects. Among several projects, you will find both the OWASP Top 10 and the OWASP Juice Shop, our intentionally vulnerable target application. Find your local chapter and take your time to join yours. There are more than 275 local chapters. Finally, check contributed content. SQL injection is one of the topics we will discuss later, but you can start reading about it at any time. In the next video, you will be introduced to the OWASP Top 10 Awareness document, one of the most popular OWASP projects. Welcome to the second part of World Wide Web Fundamentals session. In the next couple of minutes, you will be introduced to the OWASP Top 10 project and the latest published version of the awareness document. We will start with some facts about the project. Then, we will do a walk through the latest published version of the document, and we will close the session discussing how it is built. The project, by its authors' own words, the OWASP Top 10 is a standard awareness document for developers and web application security. It represents a broad consensus about the most critical security risks to web applications. The project is led by 4 well-known OWASP volunteers: Andrew, Brian, Neil, and Thorsten. With a few little changes since it was first published, the document brings security awareness to developers and managers. It was generally adopted by software industry, and there's always a huge expectation when the time comes for the next update. The document has been updated and published since 2003 and translated in several languages by volunteers. If you don't find yours, I challenge you to lead that effort. The more languages the document is translated into, the more people the message will reach. This is the project page, where you'll find a quick overview of the latest published top 10, as well as several other links. If you prefer to read the document in your own language, look for it in the Translation Efforts tab. If you're interested about the source or have a question or comment, then you should go to the GitHub repo. Better than talking, let's see how the document looks like. This is the latest published version at the time this course is being recorded. The document structure hasn't changed that much, and you may expect future versions to keep the same structure. The Release Notes section provides relevant information about how that specific version was built and how does the final top 10 compares with the previous version. Let's see how the top 10 security risks are presented in the document. Every security risk in the top 10 looks like this one. For the next 10 sessions, we will go through all the 10 security risks and we will exploit them in an intentionally vulnerable application. Let's now discuss how the top 10 is built. The process starts with a public call for data so that companies and individuals can contribute their data. Provided data should include some metadata, such as whether results came from a human-assisted tool or a tool-assisted human approach, and the list of vulnerabilities following the core common weakness enumeration. Contributed data is analyzed and normalized, and some may be subject of reclassification to group things in bigger buckets. Then comes the risk rating, which we will discuss in more detail in a few moments, but which is based on the OWASP risk assessment framework, available at owasp.org. A top 10 draft is presented to the community for discussion and contributions, what you may expect to happen in the GitHub repo. We saw a table like this during our walk through the document. Each factor, exploitability, prevalence, detectability, and technical impact, range from 1 low to 3 high. Doing this simple math, you will get the risk rating used to sort the top 10 security risks. Note that neither likelihood of the threat agent nor the business impact are taken into account. The latter is business specific, and each organization should decide how much security risk it is willing to accept. Factor ranges are given by the top 10 team. Exploitability and detectability are based on public CVEs. Prevalence is computed from contributed data, and the technical impact is an estimation. When the final document is published, all this was extensively discussed among the community, representing a broad consensus. In the next part, we will discuss how the World Wide Web works. Welcome to the third and last part of World Wide Web Fundamentals session. In this last part, we will discuss what happens behind the scenes since you type a website address into your browser's address bar until the content gets rendered on the screen. We will focus the World Wide Web architecture, clients, server, and the workflow. We will then look to the HTTP protocol in detail, and close the session with a brief overview of core web technologies. Using the World Wide Web requires 3 major components: clients, web browsers, smartphones, wearables, cars, but with Internet of Things Advanced, any connected device you can come up with. Servers, a bunch of remote computers running different software pieces that together are responsible to listen and satisfy client requests, and a communication channel, where client-server conversation happens. Let's consider our client is a web browser. We type the address, and what then? Well, first the browser needs to translate the website address, for example codered.ecouncil.org, into an IP address. The IP address is required to open a communication channel between the client and the right server. You can think of this as a Yellow Pages search. This translation is done querying special servers called DNS or domain name servers. There are plenty of them, but one doesn't know how to translate every website address. When that happens, then it will ask another DNS server until it gets a response, which is, in turn, returned to our client. After that, our client is ready to dial in the right server to request the page you've typed into the browser's address bar. All this within a few milliseconds and behind the scene. But there's a lot more. Only after accepting the client call, the client and server start talking HTTP to each other. The client says, I want codered.ecouncil.org homepage. The server reads this message and does whatever it needs to return the page to the client. Meanwhile, the client is waiting. When the server is ready to return CodeRed's homepage, then it sends the response saying everything was okay with your request, HTML below. To get the complete CodeRed's homepage, several requests and responses may be required. Whether other resources are required is a decision made by the client while processing the first and subsequent responses. The HTTP protocol is like a grammar, establishing how words should be composed together to form meaningful sentences. The HTTP protocol establishes two main sections for both requests and responses, headers and body, separated by an empty line. In this case, the body is empty, meaning that client has no content to send to the server. Get is the HTTP request method, also known as verb. There are several methods with different meanings. When the client has information to send to the server, for instance to submit a form, then the web browser uses the post method. In the link below you'll find a list with HTTP methods and what they are aimed for. The forward slash means the home page or server's main resource. If you're looking for CodeRed login page, then this becomes slash account slash login. As you may expect, HTTP has evolved since it was first proposed by Sir Tim Berners-Lee back in 1990. 1.1 is the protocol version of this message. The first HTTP version was 0.9, then 1.0, 1.1, and now there's HTTP 2. I recommend you to research the differences, especially those introduced by HTTP 2. Nowadays, a single server can host hundreds or even thousands of websites, so the client has to explicitly say what website it wants the page from. This is what the host header is for. There are several standard headers and all of them follow the host header format. Header name followed by a colon and then header value. The HTTP request method is an exception. HTTP responses have the same format as requests. They also have headers followed by an empty line and then the content, if any. The first header in the response is special, as in the request, and it is called status header. It includes the protocol version, HTTP 1.1, and the status code, 200, and the correspondent message, OK. Again, there's a list of standard status codes and messages that you should know about, and you'll find them in the link below. The content type header is used to indicate the media type of the body. In this case, the server is returning HTML, but there are several other formats like JPEG or PNG for graphics, MP3 for audio, or even JSON and XML for data exchanging. This header provides some guidance to the client so that it knows how it should handle the response. For the sake of completeness, let's talk about post requests. As said before, the HTTP post method is used when the client wants to send content to the server. It has the exact same structure we discussed before. First the headers, followed by an empty line and then the request body. Let's skip the request and host headers since we have already discussed them in great detail. The content type request header tells the server what type of data is actually being sent. In this case, we're sending data in the X www form URL encoded format. Looking to the request body, we will understand how this format works. Variable name, user, followed by an equal sign and then the variable value, John. To send multiple variables, we should repeat this pattern and concatenate everything together using ampersand as a separator. When a variable value has special characters, then the value has to be URL encoded. Exactly what happened with the pass variable value. %26 corresponds to an ampersand character, which we saw before has a special meaning as variable separator. Please note that encoding is different from encryption. Your passwords are not encrypted when sent to the server as part of a standard HTTP post request, even when you're using HTTPS. HTTPS is in fact HTTP over TLS or SSL. The word over is very important, meaning that what is encrypted is the communication channel. The protocol remains the old plain HTTP as described until now. The content length header indicates the size of the entity body in bytes. We should have 30 characters in the request body. There's a lot more about HTTP you should know, but it is out of scope. What we have discussed until now is a good starting point to help you understand most of the web application vulnerabilities out there. I strongly recommend you to read more about the HTTP protocol. Let's now briefly discuss World Wide Web core technologies. HTML stands for Hypertext Markup Language, and it is used to describe documents to be displayed in a web browser. Let's have a look how on a sample HTML page. What we have here is a simple text file with some HTML. Enclosed within angle brackets, we have tag names. Each tag name has a special meaning, and the browser knows what to do with them to render a page. For example, H1, H2, and H3 are headings, and they should appear on the screen with different font sizes. Let's have a look. Here they are, our headings, H1, H2, and H3 from top to bottom. Nowadays, web pages are far more complex than simple text, and HTML has several other elements. Let's add some to our page so that we can welcome visitors. We have just added an input text field and a button with the Say Hi label. Let's see how they look like in the browser. We have both elements on the screen, an input field where we can type our name and a button. The button does nothing by default, but we will fix it later. First, let's see how to add some color to our page. CSS stands for Cascading Style Sheets. It is a style sheet language used for describing the presentation of a document written in a markup language like HTML. Let's see how to use it. First, we will need to create a new style sheet file. We will save it as screen.css. Then, we will need to link it to our HTML page. To paint the word red in red, we will enclose it within a span tag with class red. Then we will need to go back to our style sheet and write the class definition. In this case, we want elements with class red to have the red color. Let's now see how it looks like in the browser. Now, just the button's behavior is missing. For that, we will need some JavaScript. JavaScript is a programming language that enables interactive web pages. The vast majority of websites use it for client-side page behavior, and all major web browsers have a dedicated JavaScript engine to execute it. Again, we will create a new file. This time we will call it main.js. This simple JavaScript function gets the value typed in the input field and then shows a model saying hello to our guest. Using the script tag, we load the JavaScript file into our HTML page. Then, using the onClick attribute in the button tag, we can bind the say hi function we have just written. Let's now play with our button. We're done with the World Wide Web fundamentals. You now have the basic knowledge of all web application building blocks. Remember that there's a lot more about all these topics. In the next session, we will jump into the WASP Top 10 with our first risk, injection flaws. See you there.
Did you know that you can be part of the lucrative cybersecurity industry? Even top companies like Google, Microsoft, Amazon, IBM, Facebook, and Dell all hire cybersecurity professionals. The cybersecurity industry has a 0% unemployment rate. The average salary for an entry-level cybersecurity job is about $100,000 per year in the United States. Furthermore, you don't need to know coding and learn from your home, and you get a scholarship to kickstart your career. Apply now. EC Council is pledging a $3.5 million CCT scholarship for cybersecurity career starters. Scan the QR code on the screen to apply for the scholarship. Fill out the form.
Welcome to Injection Flaws session. In this first part, we will focus on threat analysis. We will take our time to dig into injection flaws details. Then we will discuss how the system can be harmed, the impact of successful exploitation, and give you some insights to identify who may want to harm your system. Injection is a very broad concept. No better place to look for a definition than in the dictionary. Unfortunately, we don't get that much here, but keep in mind that we're talking about something that is injected, and so we need a place where to inject. Let's see what the dictionary still has to offer following some links. Following the link in the injected word, we get something far more interesting. What is injected is something arbitrary or inappropriately. In AppSec, this inappropriately something is called payload. In the next few minutes, we will do our way to find what is this something and to find the place where to inject it. We have discussed the World Wide Web architecture before, but now I want to look at it from another perspective. In the image, we call server to the whole infrastructure required to satisfy client requests, including web application firewalls, HTTP servers, backend and database servers, and even third-party services. Note that data flows through all these systems back and forth to satisfy client requests. The server is a business asset and the right place to keep valuable data such as the user database, health records, financial data, etc. Direct access to the server is expected to be reserved to authorized parties, and attackers are not supposed to be one of them. If attackers cannot directly access the server nor the data, then the best they can do is behave like a regular client. Of course, they won't get the gold from your server if they are well behaved. A traditional login feature is something implemented by the backend server which requires user input, email and password provided by a client, and a database record that matches the provided data, if any. To get unauthorized access to the system when requested to log in, instead of a valid email address, attackers will provide something inappropriately, but not arbitrary. They will provide a special crafted input which will compromise your backend or database servers. We will explore this attack scenario in detail. How does an attacker get access to the system using inappropriately something, other than a valid email address? What payload would do it? First, let's have a look into the database table where authentication credentials are stored. There are several types of databases. Our application uses a relational database management system with SQL support for data management. This is how an accounts table aimed to store authentication credentials would look like. This is an oversimplified example. Nevertheless, this is what we find quite often on vulnerable applications. Note that passwords are not the actual secrets, but their hash. If you are not familiar with the hashing concept or with password storage, please read OWASP password storage cheat sheet following the link below. To retrieve admin's record, we need to send the following SQL query to the database. If we get exactly one record, then the account exists and credentials are okay. Otherwise, the email address does not exist in the database or password is wrong. Again, this does not comply with the best practices, but it is quite common pattern found on vulnerable applications. This is how it works for the admin account, but as a feature, the email address and password can't be hard-coded, and they should take arbitrary user-provided values. This is a template for a generic query that will work for any user-provided values. What's enclosed within square brackets should be replaced on every login request with provided data. And here we have a pseudo implementation of the login feature in the backend server responsible for doing such replacements. Our query template is in the first few lines. User-provided data is available in the rec.body object variable, and it will be interpolated with the template string. If no database match is found, then record variable will be null. In such case, an error is thrown and no access is granted. Otherwise, the program flow continues and access is granted. Let's see this in action with two examples. On a legit admin login request, user provides a valid email address and the corresponding password. The backend server replaces the values in the right places and sends the query to the database server. What the database server receives is a valid query, and it will look up the accounts table for a record matching both email and password values. There is only one record in our database matching the query criteria, the admin's account. Let's now attack. Instead of a valid email address, the attacker provides a partial SQL query. Check how it looks like in the backend server, highlighted with the red background. On the right side is what the database server receives. Again, a valid SQL query. If you look closer, the search criteria is different from what we had before. We are now searching for a record with empty email or where 1 is equal to 1. Everything else after the semicolon does not belong to the first query, and so this time no match will be performed regarding the password value. Although there's no such record with empty email, every record matches the 1 equal to 1 condition. Since we're dealing with an OR, matching one criteria will be enough. The first match record will be returned to the backend server. The backend server doesn't know that password wasn't matched. Remind that the backend server is written in a programming language other than SQL, and it knows nothing about SQL. Since the backend server receives some data from the database, the variable record won't be null, and access will be granted. And voila! Admin account is often the first row in the database table, and the first match of malicious queries like the one we discussed before. This means that chances are attackers will be able to log in as admins. Now we have the answers we were looking for. Something in this case is a partial SQL query, our payload. And the place where the payload is injected is in the backend server, in the SQL query template. There are several types of injections. What we have discussed until now is called SQL injection, but injection vulnerabilities are often found in NoSQL queries, LDAP, XPath, operating system commands, XML parsers, and many more other places. They all work the same way. The backend has a template to which external data is appended and the result sent to an interpreter. Every data source represents a potential attack vector. Environment variables are something we tend to assume to be safe, but on a compromised system they are as critical as any other data input. Parameters are more obvious since they come from the client side. Whether they are provided by a user on a web form or by a native mobile app, always keep in mind that they are all external to the system. The same is valid for web services and third-party services in general. Even services provided by big corporations are subject of attacks. Handle data gathered from third parties as being potential harmful. Users are most of the time the main system actors. Whether they are external or internal to the organization, keep in mind that there are different motivations and that they can change over time. We can just focus the technical impact since the business impact is specific to the business and each organization will have to decide how much security risk it is willing to accept. As we have seen, injections may lead to unauthorized access to the system. Depending on the attack motivation and application functioning, injections may give attackers read-only access to the internal data or read-write access leading to complete data loss or corruption. If attackers are able to compromise authentication or authorization systems, then you may lose access to the application. In the worst case, you may even lose control over the system servers. Threat agents are application and business specific. To identify who the threat agents are, you should ask yourself a few questions. Focus on the impact to enumerate who would benefit from compromising the system. To whom is your data valuable? enumerate profiles of who has the knowledge to perpetrate the attack and what benefit they take from it. Don't forget to look inside your organization. Sometimes we're too much focused on external threats, and then the attack comes from the inside. You'll find this table in the OWASP Top 10. Pause the video and take your time to carefully read it. In the next part, we will exploit an injection flaw in our intentionally vulnerable application. Welcome back to Injection Flaw session. In this second part, we will exploit an injection flaw in our intentionally vulnerable application. Before the actual exploitation, I want to introduce you to OWASP Juice Shop, our intentional vulnerable application. After that, we will practice what we have discussed in the first part and bypass OWASP Juice Shop authentication, exploiting a SQL injection vulnerability. OWASP Juice Shop is yet another OWASP project led by Bion Kiminich. It's an intentionally vulnerable application aimed for application security training. There are several applications like this one, even some of them under the OWASP umbrella, but this is up to date with the latest version of the OWASP Top 10. This is the OWASP Juice Shop project page, where you'll find a lot of information about the project and the application itself. After completing this session, come back here and check the available information. For now, let's focus on the application architecture. On the left, we have the client, a web application written in JavaScript using the popular Angular framework. Juice Shop supports authentication with Google accounts. Then we have the backend, where there's an API server running, written in Node.js. The API server interfaces with the file system and the SQLite database, which support SQL for data management. If you're curious about the implementation, you can have a look into the source code in the project's repo. We will come here in the third and last part of this session, so that you can see how the vulnerable source code we will exploit next looks like. Without further delay, let's hack. If this is your first time with Juice Shop, pause the video and take a while to play with it and see what features it offers. For now, we will sign up for a regular user account. Let's now log in with our new account. But first, let's pop up Browser Developer Tools and switch to the Network tab so that we can see both client requests and server responses. The login request should be a post request with success status code, such as 200. Let's check the details. Our authentication credentials, email and password were sent as a JSON object. Server responded with a JSON object too, with several tokens and our email. Let's see our account profile and then review what happened behind the scene. The provided authentication data was sent to the backend server, where it was merged with the SQL query template and then sent to the database. Here we can see the SQL query received and executed by the database server. There's only one row in the table that matches our email and password hash. and this gave us access to our account. Now let's hack. First, we need to log out from our regular user account. Then we'll open Developer Tools, switching to the Network tab. This time, instead of providing a valid email address, we will first check what the server response is if we send a single quote character and a random password. Notice that this time the login post request has a 500 status code, internal server error. The request data is exactly what we entered in the form. The response, still in JSON format, this time is an error object, including the query sent to the database where we can see that our single quote character wasn't escaped. This means the application is vulnerable to SQL injection. Let's improve our payload and resend the login request with a random password. In the Network tab, we can see that the login request was successful. Let's check the details. We can see that what was sent was our payload and an arbitrary password. The server sent a JSON object with some tokens and the admin's email address. Let's check our account profile to confirm that we are authenticated as admin. So, what happened now? In the backend server, we can see how the client provided data was merged into the SQL query template. On the right, the final SQL query sent to the database server. Let's look at it in detail. There's no record in the table with an empty email address, but 1 is equal to 1 for every record in the table. The semicolon breaks the SQL statement, and no more conditions are checked until this statement is executed and the result returned back to the backend server. All records will be returned, but since the backend is expecting just one record, only the first one will be considered. Luckily for the attacker, the considered record is the admin one, meaning that attacker gets access to the application as administrator. In our next video, we will discuss what makes the application vulnerable and how to prevent it. Welcome to the third and last part of injection flaws session. In this last part, we will discuss injection flaws mitigation. We will start discussing what makes an application vulnerable. Since OWASP Juice Shop is open source, we will spot the vulnerable source code. Then we will discuss how to avoid such vulnerabilities. Okay, first big mistake. Juice Shop asks for an email address, but no validation was performed upon our payload. A validation such this one would have aborted the backend execution before merging submitted data with the SQL query template. Sometimes required data doesn't have a well-defined pattern as an email address, and so validation don't come easy. In such cases, the characters range should be limited and dangerous ones removed from the input or the input rejected. Client-provided data is directly concatenated to a SQL query template in and by the backend server. Remind that the backend server is written in a programming language other than SQL, so it knows nothing about how to handle SQL queries. The backend is just doing arbitrary strings concatenation. Some characters have special meaning to specific tools or contexts. In our SQL query, the single quote character is used to wrap strings like the email address. When external data is appended to the SQL query template inside single quotes, and that data contains one or more single quote characters, then the resulting query will be different from what the template was written for. To avoid this, the single quote character in the external data has to be escaped so that it is read as is with no special meaning. Escaping is not an easy task to be done externally to the target tool or context. To do it, you will need to know all special characters beforehand, and you'll certainly miss one or a few of them. Let's see what makes Juice Shop vulnerable. This is the OWASP Juice Shop project page, and we're gonna jump from here to the project repo. The project repo has all the source code, but now we are looking for a specific folder which should have all application routes. Inside this folder we should find the login.js file, which should have all the login features. We have a first login function and then a inner after login function, but this one doesn't look to have any SQL query template. In the next one we can see some select from the users table, and then the email and password both are matched against user input data. So this is a good candidate. Let's copy and paste it to our text editor and make it readable. This is how the query template looks like before interpolation. We're gonna replace the variables with the admin account details and see how the final query looks like. So this is what gets sent to the database and executed on a legit login request. Let's do the same with our payload. Since what's after the semicolon is ignored by the database server, this is the statement that gets executed. When we're dealing with SQL, prepared statements are that safety zone. Instead of concatenating a SQL template with user input data in the backend server without the right context, you'll first provide the SQL interpreter the query template with some placeholders where you expect user input data to be replaced. On a second step, you will provide the input data to replace the placeholders. But this operation will be done by the SQL interpreter, which knows its own context better than anything or anyone else. Always validate external data. When it does not meet your expectations or requirements, reject it. Make sure that provided data only has allowed characters. Whitelists tend to be safer than blacklists. You know better what you want than what you don't. As said before, escaping is not an easy task. If there's no safe API available, look for well-documented and maintained escaping libraries specific to your target interpreter. When dealing with SQL queries, always limit the number of records to return to mitigate huge data leaks in case you get compromised. In our next session, we will discuss broken authentication flaws. Until then, take your time to carefully read the injection section of OWASP Top 10. Welcome to Broken Authentication session. In this first part, we will focus on threat analysis. We will take our time to dig into authentication flaws details. Then, we will discuss how the system can be harmed, the impact of successful exploitation, and give you some insights to identify who may want to harm your system. Let's put things simple. In web applications context, authentication is the act of providing users identity. Authentication and authorization are two different things. The former is used to prove identity, and the latter, access rights. Authentication in web application context is far beyond the login form. The sign up, recover password, and the process by which the server maintains the state of the entity interacting with it, or session management, are also authentication mechanisms. To identify the party interacting with the system, such party has to provide authentication factors. Authentication factors can be grouped in these three main classes. Security research has determined that for a positive authentication, elements from at least two, and preferably all three classes, should be verified. Traditional web application forms use the weakest, single-factor authentication, just requiring a knowledge factor, the password. When passwords leak, then this knowledge becomes shared knowledge and it is no more a secret. When you're logging in, you're saying, I'm john.doe@samos.com, and to prove you that, take my password and check it against your records. The server takes your email and password and looks up the database for matching records. This is no different when someone else takes your email and password and performs the login on your behalf. Yes, it does. And on our exploitation session, we will chain several authentication flaws together to get admin access. Let's first discuss attack vectors, impact, and threat agents. A simple search for username-password combination lists will return millions of records as a result of authentication data leaks. Feeding these lists in a software tool will be enough to compromise several web applications. There are plenty of free brute force automated attacking tools. It is just a matter of setting your target application and provide the username-password list, or even just let it compute all possible combinations. The most common authentication issues are well documented and the information is generally available and easy to understand. Sometimes your own application can be used against itself. Abusing other issues, such as user enumeration, help compromising authentication. An attacker with access to a victim's account might be able to lock the victim out by replacing its email or password. Attacker can also impersonate the victim and perform system transactions. The application might not be able to distinguish between transactions initiated by the victim or the attacker. Depending on the application domain, attackers with access to victims' accounts might be able to perpetrate some kind of fraud. Attackers will always be able to gather victims' profile data. Asking for ransom is quite common nowadays. Unfortunately, you're fighting virtually anyone and anything. There are fully automated networks of computers trying to exploit authentication in several web applications, just using credential stuffing attacks based on leaked authentication data. It is fairly easy to a non-tech malicious actor to perpetrate a brute force attack such as credential stuffing. Even just stealing user profile data will be rewarding, since this data will always be valuable to someone else. Sometimes authentication flaws, such as default or weak passwords, are abused inside the organization as a way to escalate privileges. Access to sensitive information may have a huge business impact. You'll find this table in the OWASP Top 10. Pause the video and take your time to carefully read it. In the next part, we will exploit several authentication flaws in order to access the application as admin. Welcome back to Broken Authentication session. In this second part, we will exploit several authentication flaws in our intentionally vulnerable application to get access as admin. We will jump straight to the hands-on exploitation. At the end, we will wrap up exploited issues, which we will discuss in more detail in the third and last part of this session. Let's hack. Let's start creating a regular user account. Before submitting the request, let's pop up Developer Tools so that we can monitor the network traffic. This should be the signup request. Let's have a look into the request details. The request body includes our account details, where we can see our weak password. We can now log in. Next, we will try to recover our own password. Again, let's first pop up Developer Tools. While we were typing, several requests were made to the security-question endpoint. Let's inspect the last one, which has our complete email address. Our email address was sent in the request, and the server returned our security question. How does the server response looks like for an email address which does not belong to a Jewish shop account? This time the response is empty. Based on these binary responses, we can check whether there's an admin account. Comparing this response with the one we've got with our own email address, we know that such account exists and we can try to log in. We don't know the password, but at least we can try to guess it. Of course it's wrong, but we can do better. Let's search for common web admin passwords. Let's try the first ones with at least 5 characters, since we saw that this is the minimum required in the sign up. Doing these one by one will take long, but this is exactly the type of task computers are great doing. This simple bash script does concurrent requests to the login endpoint based on a given email address and a list of passwords. It will stop on a successful login attempt or at the end of the passwords list. Let's move the passwords list into a text file and do some cleanup. It's time to run our script with Joyce Shop admin's email address and our password list file. Two seconds was the time needed to find the password on a simple workstation. Let's now see whether it really works. In fact, it does, and we are now logged in as admin. We said that before, and now you have seen it in practice. Although there's a password strength calculator in the sign-up form, strong password policies are not enforced, allowing 5 single-class characters long passwords. The recover password mechanism can be used as an oracle to enumerate valid user accounts based on its response. And finally, the login does not implement a lockout feature based on failed login attempts, meaning that we can test as many passwords as we want for a single email address until we get the right one. In our next video, we will discuss what makes the application vulnerable and how to prevent it. Welcome to the third and last part of Broken Authentication session. In this part, we will discuss authentication flaws mitigation. We will start discussing what makes an application vulnerable, and then we will hunt OWASP Juice Shop vulnerable source code. Then we will discuss how to avoid such vulnerabilities. If your application does not enforce a strong password policy, like OWASP Juice Shop, then it is vulnerable. Showing a password strength bar is not enough. If application does nothing to detect and stop automated attacks, then sooner or later accounts will be compromised. You have seen how easy it is to get a username password combination list. OWASP Juice Shop uses a security question. We didn't exploit it, but we could have done so the same way we brute forced the password. Download a common English female first names list and keep sending requests to the application until you get a positive response. This is the worst password recovery challenge you can use. You cannot fix it. An ineffective multi-factor authentication is as bad as not having one. Sometimes multi-factor is required in the front end, but not validated by the back end. Session management is another common authentication issue. We didn't exploit it, but you'll find extensive documentation about the topic. Search and read it. Let's have a look at the source code. From OWASP Juice Shop project page, we can jump directly to the GitHub repo. Juice Shop server is bootstrapped in the server.js file. Unlike other routes, the signup one is automatically generated by an npm package called Finale. Following this approach, signup request data is passed directly to the user model, what doesn't sound like a good idea. We need to have a look at the user model to understand how the signup really works. The user model has just a schema, meaning that signup request data is saved directly into the database. Not only the password strength is not enforced, but the confirmation password matching is also missing. Let's now have a look at the security-question endpoint used to enumerate Juice Shop accounts. This is the function responsible to retrieve the security question from the database. Given an email address, it lookups the database to find the user records. If a record was found, then it searched the database for the security question record. If a security question was found, then it is returned as JSON. Otherwise, an empty JSON object is returned. This is what creates the binary feedback, allowing attackers to use the application as an oracle to enumerate user accounts. Let's now have a look at the login route. We have seen this function before on our injection flaw session. We know that this SQL query is responsible to match provided email and password against database records. If no record matching the email and password is found, then we jump straight to this else clause. In here, we just return an error code and the invalid email or password message. There's no failed login attempt counter being updated or special logging. The lack of lockout feature, rate limiting, and insufficient logging makes it possible to perpetrate brute force attacks such as the credential stuffing one we did to find the admin passwords without being noticed. If you're building a new application, then consider multi-factor authentication, since it will be easy to implement. Otherwise, if you're maintaining an existing application, changing your current implementation worth every second. Probably you won't be able to get rid of password as authentication factor. Enforce strong passwords and test them against common or leaked ones. Do not deploy or ship your application with default passwords. Otherwise, they will become shared secrets and, hey, once shared, it is no more a secret. Make sure none of the authentication mechanisms leak information about whether an account exists or not. The recover password mechanisms tend to be a good candidate for account enumeration. Make sure the response feedback remains the same regardless whether the account exists or not. Log failed login attempts. After a few, lock the account and notify the owner. Application owner should also be notified that the application or a single account is under attack. Sessions should be managed server-side. Choose a well-documented and actively maintained session management library. Audit the library specifically regarding token lifecycle. In our next session, we will discuss sensitive data exposure. Until then, take your time to carefully read the broken authentication section of OWASP Top 10. Welcome to Sensitive Data Exposure session. In this first part, we will focus on threat analysis. We will take our time to dig into sensitive data exposure flaws details. Then, we will discuss how the system can be harmed, the impact of successful exploitation, and give you some insights to identify who may want to harm your system. Unfortunately, data leaks are becoming more and more frequent. Whether data is sensitive is in general business specific, but there are some data categories considered sensitive in nature, such as authentication credentials, credit card details, and health records. Whenever data isn't properly protected at rest or in transit, either internally and over the internet, then we're dealing with a sensitive data exposure flaw. Let me show you something. This is a very simple sensitive data exposure scenario in our intentionally vulnerable web application. In the second part, we will exploit this and other issues. Notice that we access Juice Shop over HTTP and not HTTPS. This is how it works by design, but it makes it possible to someone sitting between the client and the server to spy, exfiltrate, or tamper with exchanged data. As you can see, the credit card number is masked on the screen, giving you a sense of security. Let's see how client and server exchange this data. At the bottom of the screen, you can see that the server sent all credit card details, including the number masked on the screen, in plain text. This means that if there's someone sitting between our browser and the server, then such actor already has our credit card details. Probably you'll realize that at least your internet service provider is always in such position, but proxy servers and content delivery networks are also common entities between our browsers and the web application backend servers. The credit card issue was quite obvious, but it happens a lot. Sometimes you have to exploit other vulnerabilities to uncover unprotected data, such as authentication data stored in the database. We will do it in the second part, but first let's discuss attack vectors. Attackers may not even need to touch your application to gather some sensitive data. Quite often default credentials, keys, and other tokens are pushed to public repositories. In other cases, search engines are enough to reach database backup files, logs, or other sensitive documents. Sitting between the client and the server is a privileged position to access sensitive data, but with the widespread adoption of HTTPS, attackers had to develop new techniques. Client-side attacks, such as manning the browser or scraping, are common techniques to gather sensitive data. Directly attacking cryptography is not an easy task, unless you're using old or weak algorithms or default, leaked, or weak cryptographic keys. And unfortunately, this happens quite often. When sensitive data is exfiltrated from your system, it is very likely that sooner or later it will be available in the internet or dark web. Depending on system's nature, exposed data may allow attackers to perpetrate social engineering attacks impersonating your users. Depending on the exposed data, attackers might be able to perpetrate some kind of fraud, taking advantage of systems' inability to distinguish between malicious activity and the legit one. Law enforcement is not exactly a technical impact, but rather a business impact. Nevertheless, due to data protection laws and regulations, failing to protect data may result in huge losses. There are autonomous systems crawling the web searching for publicly accessible data. Scanning public source code repositories for leaked secrets or authentication tokens became very popular. Access to sensitive data does not mean sophisticated tools and techniques. Using a search engine might be enough and virtually anyone can do it. Your data will always be valuable to someone. Attackers know that, and this is why ransom became so popular, and lots of leaked data is available for sale online. Keep in mind that those inside your organization may have privileged access to sensitive information. There are different motivations and they can change over time. You'll find this table in the OWASP Top 10. Pause the video and take your time to carefully read it. In the next part, we will exploit our target application to reach some sensitive data. Welcome back to Sensitive Data Exposure session. In this second part, we will exploit our intentionally vulnerable application to get access to some sensitive data. We will jump straight to the hands-on exploitation. Before closing, we will review what's wrong with our target application. Let's hack. First, we will create a regular user account. Before some shopping, let's configure our default address and payment methods. Alright, we are now ready to buy some juice. Let's review our order and proceed to checkout. The next steps, we should be asked to select a payment method. Let's pop up Developer Tools so that we can inspect what data is exchanged between the browser and the backend server. See how credit card number is masked in the interface. However, if we look up the request to retrieve credit card details from the server, we will find something completely different. The credit card number was sent in clear text. Since the application does not use HTTPS, anyone between client and server will be able to see it as any malware installed on client device. Let's complete our order and see how far we can go exposing sensitive data. On our first session, we exploited the SQL injection vulnerability to bypass authentication. In that case, we could not retrieve any data from the database since the backend server was just counting matched records instead of returning the actual results. If we find a vulnerable endpoint that asks for user input to merge with a query template returning found records, then chances are we will be able to access arbitrary data on the database. Usually, search features are good candidates. Why not try our luck? Let's pop up Developer Tools and search for orange, adding a trailing single quote character as we did in the injection flaws session to exploit SQL injection. Apparently nothing happened. Better opening the GET request in a new tab so that we can easily modify the queue URL parameter. Let's do it again. Okay, this time it looks promising. We now have a SQL error. The percentage character is a good sign that the SQL-like operator is being used. Let's think how the backend query template may look like. This could be the backend query template. Let's replace the input keyword with our current payload and see how it looks like. Another SQL error. This time the query is incomplete. Maybe the query template tries to match our search keyword both in product's title and description. Let's get back to our query draft and improve it. Since we're commenting everything that comes after the place where our search keyword is first interpolated, it doesn't make sense the problem is the end, unless there are some brackets around these conditions. Let's see what we get now. The same error. Maybe there's more than one bracket around the condition. Let's try with an additional bracket. Alright, now we know that we are on the right track. Until now we were able to break the query template and fix it with our own payload. We are just missing a way to join additional data to the query results. SQL allows unions between query results as long as they have the same number of fields. Let's see how many fields are retrieved for products. To be able to do a union, we need the second query to return 9 fields. Let's test it. Okay, we have our hard-coded record returned by the database server. We can now guess a table name and some fields to expose data. Table user does exist as well as the ID field. Let's try guessing other field names until we get something juicy. Finally, passwords, or at least their hashes. Vulnerable applications tend to use unsalted MD5 hashes. If this is the case, we should be able to get the original secret searching the hash we got in some rainbow table. And we got it. Let's try to log in as admin. Since we're in, why not check some addresses or credit card data? We already know the trick to expose credit card details. Let's pop up Developer Tools and reload the page. And here they are, the admin's credit cards. First, we saw that although credit card data appears masked on the screen, it is sent in clear text from the server to the client. Since the application does not implement HTTPS, someone between the client and the server, such as a proxy, will have access to that data. Exploiting a SQL injection flaw, we were able to retrieve arbitrary data from the database. We saw that sensitive data such as credit card data is not protected at rest. Finally, still exploiting the SQL injection flaw, we retrieved authentication data. Although passwords were not stored in clear text, hashing was not done properly, and we were able to retrieve some secrets using rainbow tables. In our next video, we will discuss what makes the application vulnerable and how to prevent it. Welcome to the third and last part of Sensitive Data Exposure session. In this part, we will discuss sensitive data exposure mitigation. We will start discussing what makes an application vulnerable, and then we will hunt OWASP Juice Shop vulnerable source code. Then, we will discuss how to avoid such vulnerabilities. If your application does not use secure protocols, such as HTTPS, transmitting data in clear text, internally or over the internet, then anyone in the middle will have access to the data. This is also valid for data in REST. If you're storing it in clear text, including backup files, then it is vulnerable. Hold or weak cryptographic algorithms, as well as default or weak cryptographic keys, don't do much regarding sensitive data protection. Reusing crypto keys or improper key management or rotation weakens encryption regardless the algorithm used. If your server does support encryption, but it is not enforced due to missing security directives such as HTTP security headers, then your data is at risk. The same is valid when user agent, for example a mobile app, fails to verify whether received server certificate is valid. Let's have a look at what makes Juice Shop vulnerable. From OWASP Juice Shop project page, we can jump directly to the GitHub repo. Let's first check how credit card details are handled by the server. Cards should be handled by the Finale package, and all operations pass directly to the card model. The card model implementation has just the schema, meaning that no operations are performed on user inputs before being stored or read from the database. Let's check the front-end component. Now we know where the credit card number is masked. Let's now have a look at the search feature to see the source code vulnerable to SQL injection. As seen in our first session, we have again a SQL query template, interpolated with user-provided data without proper scaping. You can now better understand the need for brackets in our payload. Let's move forward and see how passwords are stored on signup. We're looking for requests made to the user's endpoint. Apparently, signup is handled by the final package, passing data directly to the user model. Let's have a look. Okay, the password hash is computed when setting the user model's password property value. The insecurity hash function is used. Let's check it. Finally, we have found how password hashes are computed, using MD5 with no salt. Let's discuss how to mitigate these issues. Start classifying all processed, stored, and transmitted data. Identify which data is sensitive according to privacy laws, regulations, and business needs. Then apply the appropriate controls as per the classification. Data that is not retained cannot be stolen. Discard unnecessary data as soon as possible or use tokenization or truncation to avoid sensitive data exposure. Choose up-to-date and strong standard algorithms, protocols, and keys. Encrypt sensitive data at rest. For passwords, use strong adaptive and salted hashing functions. For in-transit data, use secure protocols such as TLS. Disable caching for responses that contain sensitive data. In our next session, we will discuss XXE, XML External Entities flaws. Until then, take your time to carefully read the sensitive data exposure section of OWASP Top 10. Welcome to the XML External Entities session. In this first part, we will focus on threat analysis. We will take our time to dig into XML format, XML External Entities feature, and the XXE processing flaws details. Then we will discuss how the system can be harmed, the impact of successful exploitation, and give you some insights to identify who may want to harm your system. Let's do this step by step, starting from the beginning. XML, or Extensible Markup Language, is a markup language that defines a document format that is both human and machine readable. How does it look like? As you surely agree, this is definitely human readable. We have a books catalog with two entries, Book ID 1, the OWASP Top 10 27th in edition with several metadata, and Book ID 2 just with information about its author and title. This format is also machine readable by a specific type of software, processors. Processors take XML as input, walking through the content to build a structural representation of the input. This representation can be manipulated more easily for example, storing data in a database or output it in another format such as HTML. While doing this, processors can also do some additional tasks based on the input directives. The XML standard defines a concept called entity, which is a storage unit of some type. External entities point to local or remote content using a URI. Then, the processor is responsible to request such URI and replace occurrences of the named external entity in the document by the retrieved content. This is how it works. We declare our external entity desk1, whose content should be loaded from the description.txt file. The processor requests the file content, and then, while walking through the XML document, whenever desk1 entity is found, it gets replaced by the loaded content. You may already know where this will end up. Assuming you are accepting XML file uploads to show their content in your web application, then chances are a malicious user will be able to read arbitrary files from your system using this technique. We will see this in action in the second part. To exploit XML external entities processing, attackers should be able to upload malicious XML documents, inject hostile data in existing XML templates processed by the system, or use integrated systems and services to retrieve remote hostile data. Abusing vulnerable XML processors may allow attackers to gather local data relative to the system where the processor is running. Since server-side request forgery is also possible, attackers may be able to gather other internal content via HTTP or HTTPS. XXE can also be used to perform port scanning to enumerate and fingerprint other internal systems. Such information may allow the attacker to find other vulnerable systems. Accessing local resources that do not stop returning data, or creating some sort of XML entity circular reference can lead to denial of service. This attack is commonly referred to as the billion loth attack. It's also worth mentioning that under certain circumstances, XXE may allow remote code execution in the system where the XML processor runs. Based on the impact, your threat agents may get access to data, system information, or even control the system in case where the remote code execution is possible. Your data will always be valuable to someone, either a malicious actor looking for ransom, nation state, competitors, or activists highly motivated to spy what you're doing. You'll find this table in the OWASP Top 10. Pause the video and take your time to carefully read it. In the next part, we will exploit our target application to reach some sensitive data. Welcome back to XML External Entities session. In this second part, we will exploit our intentionally vulnerable application to get access to some sensitive data. We will jump straight to the hands-on exploitation and then move on to the mitigation part. We should look for some upload features so that we can upload a malicious XML file. Let's see what features anonymous users have access to. The customer feedback form does not allow any uploads, and as anonymous users, we don't have that much features. Let's sign up for a regular user account. Okay, let's check the same features, but now as authenticated users. Customer feedback form remains the same. Complaint is a new feature. And this time it looks like we will be able to upload some files. Let's prepare something. This is our malicious XML file. We declare an external entity, XXE, whose content should be loaded from a specific file. This file is where Linux systems store user account information. If XML files are allowed and processed by a vulnerable XML processor, then it should load a file and replace our entity inside the message tag by its content. Let's open Developer Tools so that we can inspect network traffic. Apparently, XML is not an expectable upload format, but let's see what happens. We've got an error message. Let's inspect it. The request includes our XML file content, and the response shows an error message. It looks like our XML file content is partially returned as part of the error message. Inside the message tag, we have the content of the passwd file. Let's see what else we can get from the system. Fingerprinting the operating system can be interesting. Again, the same HTTP error response. We also get the same error message, including our XML file content and information about the operating system Joystrap is running on. We could keep going gathering content from the server, but let's move forward. In the third and last part of this session, we will discuss XML external entities mitigation. Welcome to the third and last part of XML external entity session. In this part, we will discuss XML external entities flaws mitigation. We will start discussing what makes an application vulnerable, and then we will hunt OWASP Joystrap vulnerable source code. Before closing the session, we will discuss how to avoid such vulnerabilities. If an application accepts XML directly, allows XML file uploads, or arbitrary input data to be inserted into XML templates, later parsed by an XML processor, then it might be vulnerable. If any of the XML processors in the application or other integrated service is outdated or has DTD, document type definition, enabled, then the application may be vulnerable or at risk. Security assertion markup language uses XML. If you're using it for single sign-on, then your application might be vulnerable. SOAP prior to version 1.2, when XML entities are passed to the SOAP framework, are likely vulnerable to XXC. Let's have a look at the source code. From project page, we can jump directly to the GitHub repo and find the file upload route. This is the function that handles the XML upload. XML_doc is the result of calling parseXML function, passing in the upload file content. Several options are passed to the function. NoEnt is the most suggestive one. Let's find package documentation and see what this option does. The XML processor is part of the libxml.js2 package. Parse XML string function sounds like what we are looking for. Let's see what options does it accept. The no-end option. When set to true, entities occurrences will be replaced by the content they hold, previously retrieved by the processor from the resource they point to. This is what makes Juice Shop vulnerable. It should be set to false to prevent XXC attacks. Make sure that all XML processors and libraries in use by the application or on the underlying operating system are up to date and latest security patches were applied. Upgrade SOAP to SOAP 1.2 or higher. Disable XML external entities and document type definition features in all XML processors. Check the OWASP cheat sheet XXC prevention to get more details on how to do it for several programming languages and frameworks. Proper server-side input validation, filtering, and sanitization are mandatory to prevent hostile data to be included in XML documents, headers, or other integrated systems. In our next session, we will discuss broken access control flaws. Until then, take your time to carefully read the XML external entity section of OWASP Top 10. Welcome to Broken Access Control session. In this first part, we will focus on threat analysis. We will take our time to dig into access control flaws details, and then we will discuss how the system can be harmed, the impact of successful exploitation, and give you some insights to identify who may want to harm your system. Authentication and access control are often combined in a single operation, causing a serious misunderstanding regarding control's boundaries. We have already discussed authentication flaws. In this session, we will just focus authorization, whereby the system makes a decision to grant or reject access to requested resources from an already authenticated user, based on what the user is authorized to do. Anonymous users are also subject of access control. Although the system is not able to check their identity, authorization checks should be performed just like for any other user or user role. To make sure that there is no doubt, authorization and authentication are two different things. There are several access control models, but role-based access control is the most common one in web applications since it addresses most commercial and government organizations' needs. Role-based access control is defined around roles, such as anonymous user, customer, or admin, and privileges, or what they can do: read, write, update, or delete some resource, or execute some function. This may sound simple, but it tends to become complex when we start adding roles hierarchy or fine-grained privileges. Better than showing complex data flow diagrams, we will exploit different authorization issues in our intentionally vulnerable application. Access control mechanisms of old applications left running and public accessible tend to be broken or outdated, thus easier to exploit. Some applications rely on obscurity to hide administrative endpoints from regular users, assuming that only admins know the address. Some guesswork and available word lists and automatic tools are enough to uncover such endpoints. Perimeter pollution is a technique that may allow attackers to bypass access control mechanisms just by playing around with URL query string parameters, cookies, or request body. Some business logic requires actions to be performed in a certain order. Since HTTP is stateless, then it is up to the backend to track whether those actions are performed in the required order. Messing with actions order may trick the access control mechanism. Accessing other users' data may expose sensitive data such as PII and financial or health records. Compromising admin-level functions may expose all user data. If privilege levels do not distinguish users who can only view data and those who can modify it, then attackers may be able to modify other users' data, creating some sort of inconsistency or severe data losses. Sometimes attackers manage to execute actions as other users, or even higher level functions. If the system fails to distinguish malicious activity from legit one, then attackers will be able to perpetrate all sorts of fraud. As with several other flaws we have already discussed, access control ones not only allow attackers to access data, but also execute actions on users' behalf. Just considering the confidential or sensitive data exposure issue, you should think about who, individuals or organizations, may benefit from accessing your users' data. Nation-state, competitors, or activists may be among them. The ability to execute actions on users' behalf is attractive to fraudsters. Depending on what administrative functionalities your system has, malicious actors may be able to hijack the whole system or take advantage of it to perpetrate other attacks against other systems of yours or even third-party ones. You'll find this table in the OWASP Top 10. Pause the video and take your time to carefully read it. In the next part, we will exploit several access control flaws in order to access some sensitive data and execute administrative functions. Welcome back to Broken Access Control session. In this second part, we will exploit different authorization issues in our intentionally vulnerable application. We will jump straight to the hands-on exploitation and then move on to the mitigation part. We want to exploit authorization issues to access other users' data or execute actions on their behalf. We should look for some feature allowing users to submit data to the system and maybe retrieve it back. Since we don't have an account yet, let's see what anonymous users can do. Customer feedback seems to be available to anonymous users, allowing them to submit some comment and rating. Let's pop up developer tools to be able to inspect network traffic and then submit some feedback. We have here a post request to Feedback's API endpoint, and we got a successful HTTP response status code. Let's see the details. Our comment and rating were sent as part of the request. As response, we got another JSON object, which includes our submitted data and several other metadata. Since it was anonymous feedback, it makes sense user ID to be null. From what we got as response, it sounds like submitted feedback is given a unique identifier. Having such identifier is useful when we want to perform actions upon a specific record. We can take advantage of REST API's predictive nature and issue what could be a request to retrieve our feedback object back from the API. Instead of a POST request, we should issue a GET request and append record identifier to the path. We got a 401 HTTP status code, meaning that there was an error processing our request. Based on the error message, it looks like we need to be authenticated to perform such action. Let's create an account and log in. Let's now provide some feedback, but this time authenticated as a regular user. We can see the initial request to send our feedback to the server. Like before, we have our comment and rating as part of the request body, but this time we also have our user ID. The response is similar to what we had before, but again, it also includes our user ID. Note that this feedback received ID number 9, making feedback identifier sound sequential. Let's try to retrieve this feedback record back from the server. Again, instead of a post request, we should issue a GET and append the feedback ID to the path. This time we got a 200 status code. Let's inspect the response. We've got our feedback back from the server. What about our anonymous feedback? Since we know its ID, let's see if we can access it. A success HTTP status code as before. And in fact, we were able to retrieve the feedback from the server. Strange. Since the feedback identifiers are sequential, we can keep going and see what else we can get. Another anonymous feedback. Let's try another one. Okay, another anonymous feedback. Until now we were able to retrieve our own feedback and a few other anonymous records. Definitely there's something wrong with the access control. Let's keep going. Alright, finally some non-anonymous feedback. Now we are sure that access control is definitely broken. If we can retrieve other users' feedback, maybe we can also delete it. Instead of a GET request, this time we will issue a delete. Apparently the record was successfully deleted. Trying to retrieve it back from the server should fail. And it did. Not only we were able to retrieve other users' feedback, but we were also able to delete it. Actions that should be available to Juice Shop admins only. Definitely, the access control is broken. You'll certainly find other issues. Next, we will discuss what makes the application vulnerable and how to prevent it. Welcome to the third and last part of Broken Access Control session. In this part, we will discuss broken access control mitigation. We will start discussing what makes an application vulnerable, and then we will hunt OWASP Juice Shop vulnerable source code. Before closing this session, we will discuss how to avoid such vulnerabilities. In our target application, managing customer feedback are actions reserved to administrators. We saw that directly requesting specific routes or manipulating the HTTP verb, we could execute those same actions. Some applications trust that because addresses to access specific pages are not known, they are reserved to those who knows the URL. Security through obscurity is a misconception, and there are plenty of word lists and automatic tools to help uncovering such hidden addresses. Misconfigured cross-origin resource sharing policies may allow access to resources from unauthorized origins. In such situations, attackers who are able to drive victims to visit a website under their control will be able to interact with the application behind the scene and on victims' behalf. If untrusted data, just as values from cookies or hidden fields, drive access control decisions, then the application is likely vulnerable. Let's review Juice Shop vulnerable source code. From projects page, we will jump to the GitHub repo. First, we want to see how the feedbacks API endpoint is set up in the server.js file. Regardless the HTTP verb, when a request is made to the feedbacks API endpoint with an identifier, the isAuthorized method of the insecurity library is called. Let's check its implementation. IsAuthorized is a simple function that calls the express JWT function. The express JWT function is provided by the npm express JWT package. According to the documentation, this package does nothing else than validate the JSON Web Token. No ownership validation is performed upon the requested resources, and this is why we were able to access and delete other users' feedback. Let's see if there's something else in the server.js file. Requests to create, retrieve, and delete feedback records are passed directly to the feedback model. Let's see its implementation. The implementation has no additional access control validations. Let's discuss how to prevent this type of flaws. You should always follow the principle of least privilege. In particular abstraction layer of a computing environment, every module, such as a user, must be able to access only the information and resources that are necessary for its legitimate purpose. Deny access by default except for public resources. Building and using a centralized access control mechanism will make your life easier, not only managing privileges, but also discovering and fixing bugs. Log access control failures with enough details, and alert the administrators so that they can act in a timely fashion when required. Implement rate limiting to minimize the amount of data exposed by a single endpoint in case of a broken access control issue. In our next session, we will discuss security misconfigurations. Until then, take your time to carefully read the broken access control section of OWASP Top 10. Welcome to Security Misconfiguration session. In this first part, we will focus on threat analysis. We will take our time to discuss how security misconfigurations compromise application security. Then, we will discuss how the system can be harmed, the impact of successful exploitation, and give you some insights to identify who may want to harm your system. Security misconfiguration is a very broad category. By definition, a misconfiguration is an incorrect or inappropriate configuration. But security-wise, these incorrect or inappropriate configurations lower system resilience, increasing the overall security risk. Things like enable directory listing, public accessible system logs, or unhandled errors with overly informative messages fit in this category. All of them tend to give attackers insights about system internals, making further exploitation easier. Instead of searching for a zero-day vulnerability, attackers tend to take the short path first, searching for known issues. This approach has proved to be fruitful. Most applications, such as database servers, have default accounts with administrative privileges to allow the initial setup. Not removing such accounts leave the door wide open to attackers. Sometimes, special pages are used to automate specific tasks. Graphical installers are a good example. They are intended to be used once and then removed, but quite often they get deployed along with the application. Enable directory listings or public accessible files such as system logs or backups are easy to find even without touching the application. The most common consequence of security misconfigurations is the unauthorized access to some system data or functionality. Depending on exposed data or functionality nature, exploitation may become easier. Occasionally, security misconfigurations allow attackers to get control over the system. Firewall or remote access misconfigurations are good candidates to make the system vulnerable. Finding security misconfigurations can be done without touching the application. Using a search engine may be enough to identify exposed directories or files, such as system logs or database backups. Non-tech threat agents, such as competitors or activists, may follow this approach to get access to your system details or business secrets without much effort. You'll find this table in OWASP Top 10. Pause the video and take your time to carefully read it. In the next part, we will review some security misconfigurations in our target application found in previous sessions while exploiting other vulnerabilities. Welcome back to Security Misconfiguration session. In this second part, we will review some security misconfigurations we have already found in previous hands-on exploitations. We will jump straight to our intentionally vulnerable application and then move to the mitigation part. In our first session, we exploited the SQL injection vulnerability in the login form. At that time, we also found a security misconfiguration, but we didn't give it too much attention. Let's do it now. As in our first session, submitting our payload returned an internal server error response. Let's check the response body. We got a JSON object, which we will copy to our text editor so that we can read it easily. The return JSON has a single top-level property called error, which includes several other properties and values that we will carefully analyze to compile information about our target system. Starting with the message property, we see that the error was triggered by the database engine, which we now know that is a SQLite. Let's keep track of system knowledge we get from this error message. The syntax error happens near this string, which is not something we have submitted. In fact, it looks like a hash. We will find several hash algorithms detectors online. Let's try one of them. So we now know that passwords are hashed using the MD5 algorithm. Next we have stack trace. Stack traces give us a few execution steps immediately before an exception has occurred. In this case, based on the called script path, we know the application location in the file system. We also know the application is written in Node.js, based on the node_modules folder in the path. The same way, we know that the implementation uses the npm sequelize package. Continuing through the JSON error object, we can even find the exact SQL query sent to the database. And now we also know that there's a users table which has at least 3 fields: email, password, and deleted at. There are other implementation details we may assume based on the error message. For instance, because of the delete at table field, user accounts shall not be really deleted, but instead soft deleted or flagged as deleted. In our XML external entity session, XXC exploitation was only possible due to a security misconfiguration. Let's check it. While authenticated as a regular user, we have access to the complaint feature, which allows invoice uploads. We used it before to upload our malicious XML file. This business-to-business feature has been deprecated, but the upload and the XML processing is still possible. Next, we will discuss what makes the application vulnerable and how to prevent it. Welcome to the third and last part of security misconfiguration session. In this part, we will discuss security misconfiguration mitigation. We will start discussing what makes an application vulnerable, and then we will hunt OWASP just shop vulnerable source code. Before closing this session, we will discuss how to avoid such vulnerabilities. Only required services, ports, pages, accounts and privileges should be installed and enabled. Otherwise, the attack surface will be wider and more difficult to protect. Typically, default accounts and their passwords are public knowledge since they are documented. Deploying the application with such accounts enabled leave the door wide open to attackers. Overly informative error messages provide attackers better understanding of the target application. Security settings of some system components, such as application frameworks or databases, are not set to secure values. Latest security features are missing, disabled, or not configured securely. All this leaves the application vulnerable. If the server does not send appropriate security headers or directives, or they are not set to secure values, then both the client and client-server communication are at risk. Let's have a look at the source code. From projects page, we will jump straight to GitHub repo. Let's first check the security misconfiguration in the login endpoint. Post requests to the login endpoint are handled by the login function. This function is provided by the login.js file in the routes folder. This is where everything happens. First, the SQLize query, which returns a promise. If the query succeeds, returning 0 or more records, then execution continues here. When the SQLize query fails, with an error, then it is caught here and the error passed to the Express framework. We need to see how the framework is handling errors. Let's get back to the server.js file. Okay, this is the error handling setup. Errors are handled by the error handler middleware. And the error handler middleware is provided by the npm error handler package. Let's check its documentation. Reading the first line should give us a good idea of what is going on. This is a development-only middleware. Then it continues. Full error stack traces and internal details of any object passed to this middleware will be sent back to the client. Of course, this is not the right error handler middleware to have in a production environment. Let's get back to the repo and check the misconfiguration we found in the complaint feature. Complaints file uploads are handled here. The root is past several middleware functions, but XML uploads are handled by the handle XML upload function. This is interesting. It looks like that to disable the feature, someone came to the implementation and forced returning the 410 status code error with the custom message, leaving the original implementation untouched. Let's discuss mitigation. An automated and repeatable hardening process will allow to create similar environments. Note that accounts should be different or at least use different credentials. Deploy only what is really required, without any unnecessary features, components, documentation, and samples. Security configurations of every component should be reviewed and updated as part of the patch management process, in particular cloud storage permissions. Orphan AWS S3 buckets lead to subdomain takeover. Segmented application architectures provide effective secure separation between components or tenants. Containerization and cloud security groups make the task easier. Enforce client-side security, configuring security headers with secure values to be sent as part of responses. Security settings and configurations should be continuously verified and tested in all environments. In our next session, we will discuss XSS or cross-site scripting. Until then, take your time to carefully read the security misconfiguration section of OWASP Top 10. Welcome to cross-site scripting session. In this first part, we will focus on threat analysis. We will take our time to discuss cross-site scripting details. Then, we will discuss how the system can be harmed, the impact of successful exploitation, and give you some insights to identify who may want to harm your system. XXS or cross-site scripting is a type of injection in which malicious scripts are injected into otherwise benign and trusted websites. We have already discussed injection flaws, but cross-site scripting was so prevalent and specific that it was given its own category in the OWASP Top 10. It has remained in the top 10 for several editions. Although it has dropped from 3rd to 7th in the 2017 Top 10, it is still the second most prevalent issue, affecting around 2/3 of all applications. Let's see how it works. In this picture, we're searching for banana juice. We first typed the keyword banana in the search field, the page was reloaded, and the results matching our search criteria rendered on the screen. The red arrows point to places where our keyword appears on the page. Let's see this in terms of HTTP requests and responses. After typing our search keyword, banana, an HTTP request is made to the server. Client issues a GET request and our keyword is sent as a query string parameter Q. When the server receives the request, it reads the query string parameter, runs a database query to retrieve records matching our search criteria, and then computes the final HTML output to be rendered client-side, with all matching records. Then the server responds to the client, sending the final HTML to be rendered. Note that our keyword is also outputted as part of the HTML. And this is where troubles begin. What if, instead searching for banana, we decide to search for an HTML tag? From the request point of view, everything remains the same. The server may not find any matching records in the database, but it still outputs our searching keywords next to search results title as highlighted with the red background. When the browser receives the HTML to render, it doesn't know that the highlighted part was provided as part of the request. It just knows that the server sends this HTML to be rendered. The HTML tag script has a special meaning, and the code inside the tag is executed as JavaScript, popping up the modal box saying XXS. In this scenario, sharing the URL with other users will trigger the same behavior in their browsers, meaning that we can run arbitrary code remotely. There are two main types of XXS. Server XXS is exactly what we have discussed until now. User-supplied data, our search keyword, is included in an HTML response generated by the server. In the described scenario, our search keyword is not stored anywhere in the server. It is sent as part of the request and returned in the response. Due to this fact, it is called reflected server XXS. If it was stored somewhere, such as in a database, and later included in another response, such as a product reviews, then it would be called stored XSS. The other type is client XSS. In this case, untrusted data such as a user-supplied data is used to update the DOM using an unsafe JavaScript call. Imagine that web application uses an API to perform product search. In this case, the server responds with a JSON object including the list of matching products. When the API responses arrives, the web application copies the content in the search input fields, appending it to the DOM, next to the search results title, and then the list of matching products. In this scenario, the XXS payload was not part of server's response. Instead, it was gathered from client-side input field and appended to the DOM. There's also reflected and stored client XXS, but you're better reading about it in the WASP website. Let's discuss about attack vectors. Let's put things simple regarding XXS attack vectors. You just have to focus on user-controlled data, regardless its source. URL parameters and form data may be the first things to come to your mind, but there's a lot more. You should realize that users control the HTTP request, and so request headers and cookies may also be sources of hostile data. Browser's local storage is another typical attack vector since malicious actors may be able to tamper with it. If your application expects file uploads, such as photos, and then you're reading the photos metadata, then it can also be used as an attack vector. Finally, a less obvious source of hostile data: external services. If the application retrieves data from other services, for example by means of APIs, malicious actors may decide to go after those third-party services, indirectly compromising your application. Any data source is a potential attack vector. Keep in mind that attackers will be able to execute code remotely on victims' browsers. The first thing attackers will look for is session tokens. If they can exfiltrate such token from a victim's browser, chances are they will be able to use it in another browser to impersonate the victim. This is called session hijacking. Even if session hijacking is not possible, attackers will be able to use JavaScript to automate tasks to scrape user data from the DOM or to do some actions on victims' behalf, such as fraudulent transactions. Being able to execute code remotely in specific pages, such as the login page, may give attackers access to credentials. There are other techniques to trick the browser and password managers to leak credentials. Among other impacts, attackers will always be able to exploit the trust relationship between the victim and the website owner, driving the former to download and install malware. Technical skills are required to identify and exploit a cross-site scripting vulnerability. Nevertheless, there are automated tools to assist this task and plenty of information about the subject. Threat agents may be after specific victims. Targeting an application administrator may allow attackers to gain control over a privileged account and access sensitive data or shut down the system. On the other hand, attackers may be interested in a particular individual, let's say a VIP. If your application manages sensitive data such as health records, a success XSS exploitation may give attackers access to sensitive information regarding that individual. XSS can also be used for widespread attacks. It happens already in the past, creating a worm effect. To identify threat agents, consider who may want to gain control over your application and how sensitive is the information your application manages and who may want to access it. You'll find this table in the OWASP Top 10. Pause the video and take your time to carefully read it. In the next part, we will exploit XSS on our intentionally vulnerable application. Welcome back to cross-site scripting session. In this second part, we will exploit a cross-site scripting vulnerability in our target application. We will jump straight to our intentionally vulnerable application and then move on to the mitigation part. As discussed in the previous part, we will test the product search feature and understand how it works and whether it is vulnerable to cross-site scripting. Let's pop up developer tools to inspect the network traffic. Note that our search keyword now also appears in the URL and in the page's body. In the network, we can see a request to a search endpoint with a queue parameter, but it does not include our search keyword. In fact, the response returns all products, and then they are filtered client-side. If we find a vulnerability, then it will be a client XXS as discussed before. Let's have a look at Pages DOM. Using another search keyword, we see that the DOM node is updated. Let's use the XXS payload we used as example in the first part of this session. The payload also appears in the URL, but this time it isn't visible next to the search results title. Nevertheless, we can find it in the DOM. The model box was not triggered, meaning that our payload was not executed. Some frameworks have X-access prevention mechanisms, and this may be the case. In such cases, we should try to bypass such mechanisms, testing different payloads. This is the original payload. Let's try something different. This time we will use an image tag with an empty source attribute, meaning that loading image will fail. In case of error, a model box with the text XXS should be shown. Let's copy and paste it in the search box. Here it is, our model box. As you can see, the payload is also in the URL. It doesn't appear in the page's body, but it was added to the DOM. Since the payload is in the URL, if we send it to another user, then it will be executed in the user's browser. Let's go a step further. First, we need to know what information is stored in the browser when we are authenticated. we have several cookies and one item in the local storage. The token is also stored as a cookie, and both are used for authentication purposes. The value is a JSON Web Token, which we can decode and see what's inside as long as the payload section is not encrypted. In this case, we can see the email, password, and role, among several other details. Let's now change our XXS payload to show tokens value in the model box instead of the word XSS. Instead of typing the payload in the search input field, we can craft a malicious URL to send to our victims. Assuming Juice Shop admin receives and visits this URL, then the model box should show the value of admin's token. Instead of opening a model box, attackers can use other techniques to receive the value on the servers controlled by them. Assuming this is what happened, let's see what an attacker can do with the token on its own browser. As you can see, there's no active session in attacker's browser. The browser doesn't have a cookie called token, so we will create one with the value stolen from victim's browser. We have to do the same in the local storage. Now, if we reload the page, we are authenticated as Joyce Shop admin. This is called session hijacking, one of XXS possible consequences, and from now on we can act on admin's behalf. Next, we will discuss what makes the application vulnerable and how to prevent it. Welcome to the third and last part of cross-site scripting session. In this part, we will discuss cross-site scripting mitigation. We will start discussing what makes an application vulnerable, and then we will hunt OWASP Juice Shop vulnerable source code. Before closing this session, we will discuss how to avoid such vulnerabilities. Applications tend to accept data from external sources, either user input or integrated third-party services. If such data is included in HTML responses without proper validation and escaping, then the application might be vulnerable. If you're using JavaScript frameworks, or you have a single-page application which uses unsafe JavaScript APIs to append attackers' controllable data to the DOM, then your application should also be vulnerable. Let's have a look at the source code. From projects page, we will jump directly to the GitHub repo. Since we're dealing with client XXS, Then we should look inside the front-end source code folder. We are interested in something search related. This script has all the search logic. This is the search component class, which has several properties. This property should hold search keywords. Let's see where it is used. Query parameter is passed to the bypass security trust HTML method implemented by the sanitizer. It is provided by the DOM sanitizer. DOM sanitizer is part of the Angular framework. Let's check the documentation. We should be at the right place. Let's find the method we're looking for. Now we know why the script didn't trigger the model. The image did because it is considered safe HTML by this method. Of course, this method is used intentionally to make the application vulnerable, but mistakes like this one are more common than you may think. Let's see how to mitigate XSS. Choose well-tested and actively maintained frameworks that automatically prevent XSS by default. Audit such frameworks to know available options and their limitations. Always escape data based on the context in the HTML output it will be included. Depending where the data will be displayed, different escaping techniques may be required. Enforce server-side that security directives are sent to clients as part of responses. Consider adding appropriate security headers. Enabling and enforcing a restrictive content security policy will help mitigating XSS, as long as there's no other exploitable vulnerability to add malicious code. In our next session, we will discuss insecure deserialization. Until then, take your time to carefully read the cross-site scripting section of OWASP Top 10. Welcome to a secure deserialization session. In this first part, we will focus on threat analysis. We will take our time to discuss what serialization and deserialization is. Then, we will discuss how the system can be harmed, the impact of successful exploitation, and give you some insights to identify who may want to harm your system. Let's start with serialization, the process of turning some object into a data format that can be restored later. Usually, this is done in order to save objects to storage or to send them as part of communications. Some programming languages have native support for serialization and deserialization, but others require external libraries to do it. Since PHP supports it natively, we will discuss the topic using some PHP snippets, but keep in mind I'm not saying that PHP is less secure than any other programming language. So, on the left, we have the person class definition. It has a private property called name, and the public constructor which accepts a name to be passed as argument to set the private property. Instances of person will be able to print their name, calling its display underscore name method. Then we have a class instance whose name is Paulo. Finally, we serialize our instance. This means that later on we may want to recreate our person instance exactly as it is now, with the same name and being able to call the display underscore name method to get it printed. And this is our serialized instance, ready to be stored or shared through some communication channel. Take your time to figure out the format. PHP uses a mostly human-readable string format with letters representing the data type and numbers representing the length of each entry. When we want to rebuild person instance from its textual representation, then we need deserialization. The reverse of serialization process, taking data structured from some format and rebuilding it into an object. If we want to deserialize custom object like our person class, then you need to have its definition. PHP provides the unserialized function to do it. It takes the textual representation, parses it, and creates an instance of a person based on the information retrieved from that representation. All this out of the box with a single line of code. Very convenient, right? The problem is, the unserialized function did it all based on what was stored in the storable data variable. A new person instance was created because that was the object type in the textual representation after the leading capital O and number 6. If the value of storable data variable is something attackers can control, for example a cookie value, then they can create instances of any other available class, providing a valid string according to PHP serialization format. Any source of user-controlled data which is deserialized by the application represents an attack vector. Typically, serialized data is stored client-side in cookies or local storage, and later sent on subsequent requests in request headers or body. If attackers can tamper such values, then they might be able to compromise the application. Serialized values are commonly stored in databases, for example session objects, or exchanged between integrated services. Exploiting deserialization, attackers might be able to access arbitrary files. Imagine that custom deserialization loads some file from file system based on provided path. Quite often, serialized data includes roles or privileged details. Modifying serialized data may allow attackers to escalate their privileges. In some cases, special crafted serialized objects may cause denial of services during deserialization. Circular references are good candidates to exploit it. In some cases, remote code execution might be possible, allowing attackers to gain control over the system. Technical skills are required to exploit insecure deserialization. Off-the-shelf exploits rarely work, requiring changes or tweaks to the underlying exploit code. Based on successful exploitation impact, threat agents may be after sensitive information or gain control over the system. Knowledge about the system internals will greatly help attackers to exploit insecure deserialization. You'll find this table in the OWASP Top 10. Pause the video and take your time to carefully read it. In the next part, we will exploit insecure deserialization on our intentionally vulnerable application. Welcome back to Insecure Deserialization session. In this second part, we will exploit insecure deserialization in our target application. We will jump straight to our intentionally vulnerable application and then move on to the mitigation part. We are about to exploit insecure deserialization in our target intentionally vulnerable application, and we will do it in a specific address, API-docs. This is a common API address where Swagger is made available. To find common addresses, you can use specific word lists. There are plenty of them available, as well as several tools to run through their entries. Swagger is an open source software framework backed by a large ecosystem of tools that helps developers design, build, document, and consume RESTful web services. What we have here is the Swagger UI, which provides documentation of available API methods, what's expected as request payload, and possible responses. This tool also allows us to test the API, issuing requests and watching responses data in place. We will need an account to test the API. We will create one and grab the authorization token to provide it to Swagger UI. We can now pick the authorization token from browser's local storage. It is just a matter of copy and paste it into Swagger UI. We should now be able to successfully execute the example request. Let's have a closer look at the example request payload. Order lines and order lines data properties are quite similar, but while the former is a JSON array, the latter is a string. In fact, the latter looks to be a JSON stringified array. We can check request data schemas documentation provided by Swagger UI. Regarding order lines data property, it says it is a customer-specific JSON format. Let's change the request and see what happens when we send a malformed order lines data property. This time we got a 500 internal server error response, and the response body includes a lot of details, such as a stack trace commonly leaked on unhandled errors. The message says A is not defined, what sounds that the API server was looking for a variable called A, meaning that the property value was executed as JavaScript. The stack trace shows that the error was thrown by the not evil node package. Let's check its documentation. In fact, based on not evil documentation, order lines data property is evaluated as JavaScript. It doesn't sound right, but it might have been used to convert the string back to array for some reason. Not only we have found an insecure deserialization, but also a remote code execution issue. Let's change our request and try some valid JavaScript. We've got a successful HTTP response. We can now try to crash the server with an infinite loop. This time we've got an internal server error response. Our infinite loop was detected and max iterations reached. This would have been enough to cause a denial of service if there was no protection in place. Next, we will discuss what makes the application vulnerable and how to prevent it. Welcome back to the third and last part of Insecure Deserialization session. In this part, we will discuss insecure deserialization mitigation. We will start discussing what makes an application vulnerable, and then we will hunt OWASP Juice Shop vulnerable source code. Before closing this session, we will discuss how to avoid such vulnerabilities. Whenever an application deserializes data supplied by external entities, such as users or third-party systems, then it is at risk. Note that user-supplied data includes HTTP request headers, cookies, query string parameters, request body data, metadata extracted from uploaded content, etc. The same way, data gathered from external systems pose a security risk. Malicious actors may go after such systems instead of directly targeting your application. Let's have a look at the source code. From Juice Shop project page, we will jump to the GitHub repo. We are looking for the server.js file, where we should find the Swagger setup as well as the B2B orders API routes. This is the Swagger UI setup. And this is the B2B API route, handled by the B2B order function, implemented in the B2B order.js file in the routes folder. Let's jump straight to the implementation. We can see here that order lines data is retrieved from the request body. Then it is passed to the safeeval function, which runs inside the sandbox. Due to the timeout option, the denial of service was not possible using the infinite loop. Let's discuss how to avoid insecure deserialization. Always avoid accepting serialized objects from untrusted sources. If you cannot avoid it, limit serialization and deserialization to primitive data types only. Implement integrity checks, such as digital signatures, on any serialized objects to prevent hostile data object creation or data tampering. Performing deserialization on a sandbox or low privilege environment helps lowering the impact of insecure deserialization flaws. Restrict network in such environments. Log deserialization exceptions and failures, especially those related to unexpected data types. Monitor deserialization, alerting whenever suspicious activity is detected, such as when a user deserializes frequently. In our next session, we will discuss using components with known vulnerabilities. Until then, take your time to carefully read the insecure deserialization section of OWASP Top 10. Welcome to Using Components with Known Vulnerabilities session. In this first part, we will focus on threat analysis. Since this topic is pretty much straightforward, we will briefly discuss it. We will also discuss how the system can be harmed, the impact of successful exploitation, and give you some insights to identify who may want to harm your system. Have you ever heard about dependency hell? If no, please check Wikipedia. Dependency hell can take several forms, and the most common in today's software, and specifically web applications, is the number of dependencies of a single application. Recent statistics say that 80% of the code in today's applications come from libraries and frameworks. Application owners not always understand the security risk dependencies represent to the overall security of their applications. The risk of vulnerabilities in these components is widely ignored and underappreciated. Dependency management has been for a long time a big challenge. This table gives you an overview of the top 5 most dependent upon NPM package, the same technology used by our intentionally vulnerable application. Notice the number of dependent packages. Can you imagine how many applications will be affected by a single vulnerability in one of these packages? The request package, highlighted in red, was deprecated by its author and it is still being heavily downloaded. Check the weekly downloads. I think you now understand how big this problem is. Let's move on. When you realize that your application is made of several building blocks and some of them are third-party software, you'll have a good idea of the potential attack vectors. Nowadays, web applications rely on several free and open source components developed and maintained by several individuals, distributed on external registries, but without any warranty. Some of these components are not well maintained and others were even abandoned by their authors. Attackers may try to add backdoors to popular components, contributing with some source code which is not properly reviewed and ends up delivered as part of the component. They can also publish their own malicious libraries or packages in the official registry, disguised as some useful functionality. Attackers can also go after registries' accounts, gaining control over popular components' owner's account. When this happens, and it already happened in the past, attackers can modify the component being delivered. It's not easy to define the impact of using components with known vulnerabilities. Components, such as libraries, frameworks, and other software modules, run with the same privileges as the application, what may undermine application defenses and enable various attacks and impacts. Introduced vulnerabilities can be of any type. They can lead not only to severe data losses, allowing attackers to bypass authentication mechanisms, escalate privileges, or accessing arbitrary files, but also to full system takeover via remote code execution or providing access to remote administrative interfaces. It is fairly easy to find already written exploits for known vulnerabilities. There are automated tools to test known vulnerabilities with available exploits in a target application. This makes the task simple even for non-so-technical people. Most applications rely on third-party code, either libraries, modules, or packages. Anyone contributing to such dependencies may introduce backdoors. You'll find this table in the OWASP Top 10. Pause the video and take your time to carefully read it. In the next part, we will exploit a component of our intentionally vulnerable application which has a known vulnerability. Welcome back to Using Components with Known Vulnerabilities session. In this second part, we will exploit a known vulnerability in our target application. We will jump straight to our intentionally vulnerable application and then move on to the mitigation part. In previous sessions, we have seen that Choose Shop used JSON Web Tokens to store some number of claims. These tokens are stored client-side as cookies and in browser's local storage. There's a well-known vulnerability in some JSON Web Token libraries, allowing attackers to bypass the verification step. Let's check whether Juice Shop is vulnerable. To do that, we will first create a regular user account and log in to get a valid JSON Web Token. We can now retrieve our JSON Web Token from browser's cookies or local storage. Next, we will decode our JSON Web Token. JSON Web Tokens have three sections, all of them base64 encoded and split by a dot. The first section is called header, and it includes information about token type and the algorithm used to compute token signature. The second section is called payload, and it holds the actual data or claims. The third and last section is the signature. Tokens can be signed by the server using a key, so the server is able to verify that the token is legitimate when it is sent back by the client in subsequent requests. The signature is calculated by base64 URL encoding the header and payload, concatenating them with a period as a separator, and passing the resulting value to an algorithm such as the HMAC SHA-256 with a secret. The name of the algorithm used to compute the signature is what goes into the JSON Web Token header, so that the same algorithm can be used to verify tokens' authenticity. This was a quick overview of JSON Web Tokens, but you're better reading more about this since JSON Web Tokens are very popular and its use widespread. So, now let's talk about the JWT Common Libraries vulnerability we will try to exploit. JWT libraries have to implement at least two mandatory signing algorithms, none and HS256. The none algorithm is a curious addition to JWT. It is intended to be used for situations where the integrity of the token has already been verified. Some libraries treated tokens signed with the none algorithm as a valid token with a verified signature. You must be seeing where this is going. We will replace the alg property in the JWT header of our token by none, then change some data in the payload section and remove the signature. If Juice Shop is vulnerable, our tempered JWT should be accepted. Let's copy and paste the JWT header into our terminal to decode it. Now we copy the decoded header, modify the alg property, and encode it back using base64 command line tool. Let's copy and paste the new header into our text editor, appending a dot to separate it from the payload section we will append here later. We need to do the same with the payload. Let's copy and paste it into our terminal so that we can decode it. Now, We copy and paste the decoded payload, modify the email property to something that should not exist in Juice Shop database, and encode the modified JSON payload using base64. Again, let's copy and paste the outcome into our text editor. We won't add a signature, since our token is not signed according to our new JWT header. Now we're gonna replace the token in our browser's cookies and local storage with our crafted JSON Web Token. Let's now access some pages and see whether Juice Shop accepts our crafted JSON Web Token. As you can see, the complaint form shows the email address we replaced in the JSON Web Token. Let's see if we can post a message. It looks like we have done it. Let's check the customer feedback feature. It also shows the email address we replaced in the JSON Web Token. Let's also post some feedback. Based on what we have experienced, the JSON Web Token library used by Juice Shop is vulnerable. Next, we will discuss what makes the application vulnerable and how to prevent it. Welcome to the third and last part of using components with known vulnerabilities session. In this part, we will discuss mitigation. We will start discussing what makes an application vulnerable, and then we will hunt OWASP Juice Shop vulnerable source code. Before closing this session, we will discuss how to avoid such vulnerabilities. Not knowing what components and respective versions your application depends upon, directly or indirectly, both client and server side, makes it vulnerable. Software that is vulnerable, unsupported, or out of date leaves the application vulnerable. Frameworks, libraries, and modules tend to run with the same level of privileges than the application itself. If components configurations are not set to secure values, then your application is at risk. We have discussed security misconfigurations already. If vulnerability scanning is not performed frequently, then components vulnerabilities may pass unnoticed. The same is valid if you do not subscribe security bulletins related to components in use. New vulnerabilities and exploits are found and published all the time. Of course, if you do not patch, update, nor upgrade components in a timely fashion, then your application is at risk. Performing such tasks without proper compatibility testing may also put application at risk. Let's have a look at the source code. From Juice Shop project page, we will jump to the GitHub repo. We're looking for the server.js file where application setup is performed. We are now looking for some authenticated root, since this is what Juice Shop uses JWT for. The isAuthorized method from insecurity looks to be what we are looking for. Let's have a look at the implementation. The isAuthorized method is just a wrapper around the express JWT function. Express JWT is provided by the express-jwt package. Let's first check what version is used by JuiceShop, checking the package.json file in the root folder. The package.json file has the inventory of required dependencies, and we should find here the express-jwt. JuiceShop uses the 0.1.3 version. Let's now check packages documentation. JuiceShop is definitely using a very old version of this package. Current version is 6.0.0. Let's check packages issues on GitHub, searching for security-related ones. This one seems to be exactly the reason why JuiceShop is vulnerable. Express-JWT versions prior to 0.2.2 were vulnerable, and we saw that JuiceShop still uses one of those versions. Let's talk about how to mitigate these issues. Restrict your dependencies to the bare minimum. Audit every dependency before adding it to your application. Remove unused dependencies, unnecessary featured components, files, and documentation. What is not there cannot hurt your application. Continuously inventory client and server-side components and their versions, as well their own dependencies. Monitor sources like CVE and NVD for vulnerabilities in components that belong to your inventory. Obtain components only from trusted sources over a secure connection. Prefer signed packages to avoid installing modified malicious components. Monitor unmaintained libraries and components, as well as those that do not provide security patches for old versions belonging to your inventory. In our next session, we will discuss insufficient logging and monitoring. Until then, take your time to carefully read the Using Components with Non-Vulnerabilities section of OWASP Top 10.